So I see people are still joining, but I think we can get started. So hi, everyone. Welcome to the Essex Seminar Series. I'm Cassie Medley. I'll be moderating the seminar today. Today, I'm super excited to welcome our speaker, Timothy Cronin from MIT, who's going to be talking to us about hurricane dynamics. Just as a note, the seminar is recorded, and our recording will be on our YouTube channel in just a couple days. So a couple words about the speaker. Tim Cronin is an associate professor of atmospheric science at MIT. He and his group combine theory and idealized numerical modeling experiments to understand the dynamics of Earth's atmosphere and the stability of the climate system. Professor Cronin has worked on a wide range of subjects in atmospheric and climate sciences, ranging from understanding the basic state of the high-latitude atmosphere and its sensitivity to global change, to rainfall extremes and convective organization in the tropics, to the physics of the runaway greenhouse in worlds with different atmospheric composition. He received his PhD from MIT in 2014 and was a NOAA Global Change postdoctoral fellow at Harvard University from 2014 to 2016. So without further ado, I will go ahead and pass it along. Thanks.
Okay, thanks very much for the invitation and for the introduction, Cassie. So I want to talk today about some, first off as well, I want to say I'm happy to take questions if anyone has them in the chat during the time. I will try to monitor that as well. I know that as a moderator, Cassie's allowed to do that, but I've taught enough classes on Zoom that I'm fine with people asking questions in the chat. So I want to talk today about some very idealized modeling work that I've done over the past few years and some bridging recently into some actually experimental stuff that I won't talk about, but simulating rotating atmospheric convection under a range of dry to moist conditions. So the combination of planetary rotation and moist convection leads to the dramatic phenomenon of hurricanes or tropical cyclones in Earth's atmosphere. And hurricanes in Earth's present climate are inextricably tied to water. So the way we portray them does that justice. The way we show hurricanes is vividly connected to how they have mobilized atmospheric water into a thick swirling cloud pattern, or how they've moved ocean or rainwaters near the surface into crashing waves or rain-blasted palm trees. And most of the damage from hurricanes comes not from their winds, but from their storm surge and freshwater flooding. So one of the basic questions that's driven my research in this area over the past few years is this: is moisture truly fundamental to the vortex dynamics of a hurricane? This might sound like nonsense in light of the previous slide. How can you imagine a hurricane without the dark looming clouds over a tropical ocean, without torrential rain, or a hurricane divorced entirely from a moist ocean surface? Well, first stab at an answer to the question based on one study from a dozen years ago is that no, you don't need moisture for a hurricane. So can people see my cursor here, or do I need to turn on the laser pointer?
We can see your cursor.
Okay, great. So they found that you could get a dry storm readily in an axisymmetric, that is a model in radius and height of the atmosphere, an axisymmetric atmospheric model, sustained by surface sensible heat fluxes, or just conduction, turbulent conduction of heat into the atmosphere from a warm underlying surface, and sustained by a large temperature jump between the background surface and the atmosphere. So I'm showing a figure here from work by Aga Moroyets and co-authors Olivier Paul-Louis and Steve Garner from a paper about a dozen years ago, where a dry storm on the left is compared to a moist storm, sort of normal storm on the right. So what's shown in the top panels is a radius height cross-section of the swirling or tangential winds of the storm, which are strongest near the surface. They decay as you go upwards and as you go outwards away from the eye wall. That's very similar in the dry model and in the moist one, though the winds in the moist model are somewhat stronger and a little more concentrated. And then on the bottom panels are shown that the radial winds are the inflow and outflow, sort of going towards the center of the storm and away from the center of the storm. And in the dry storm, there's a deep layer of inflow and then a deep layer of outflow in the upper troposphere. In the moist storm, the layer of inflow and outflow are shallower and a little bit stronger. As my advisor, Carrie Emanuel, put it, this paper was initially met in the hurricane community with deafening silence. But I think it's really fascinating, and it brings up a lot of questions for which we have few answers. So, for example, these are just a few. Are these dry hurricanes even stable in 3 dimensions? What controls their intensity, size, and structure? And do the theories that we've developed that apply to moist hurricanes apply to dry storms as well? What does the transition from moist to dry dynamics look like? Are these two end members of something that's a sort of a transition that mostly happens towards the moist end towards the dry end, or what? So the little work has been done to address these questions, and I'm going to talk about work that I've done on this today. So before I go into this in more detail, a very legitimate question you might ask is, okay, if dry hurricanes don't exist on Earth, why the heck should we care about them? My most compelling answer to this lies in simplicity and the use of model hierarchies, or sets of models of varying complexity, to better understand the real climate. So a lot of our understanding of how things like mid-latitude storms work, or how the overturning circulation, the Hadley circulation in the tropics works, comes from models that don't necessarily include all of the effects of moisture. And it would be great if we could further develop our understanding of hurricanes in a similar way. The possibility of rotating dry convection, that is convection without phase change, organizing into large-scale vortices, also suggests that experiments in a tank of water or direct numerical simulation might be able to produce these structures, these vortexes, over parts of parameter space. And I find the idea of experimentally studying hurricanes in a tank to be fascinating, both from a scientific and also potentially from a teaching standpoint. And related to this is the point that if dry rotating convection is all you need to produce hurricanes, then it may be possible to find them in simulations or experiments of just rotating Rayleigh-Benard convection, which would make a really nice linkage between the behavior of the real atmosphere and a huge body of work on convection in applied math, physics, and engineering. And finally, vortices that are like dry hurricanes might exist on other worlds or in deep past climates of Earth, even if they don't exist in Earth's present climate. So we're trying to study a phenomenon that's potentially quite general to rotating turbulent convection over a surface that has the ability to store a lot of heat. So the work I'll talk about today involves several ways of trying to explore the dynamics of hurricanes through the lens of this moist to dry continuum. So first, we've explored how storms form and their properties in what I'll talk more about, this rotating radiative convective equilibrium, where the convective heating of the atmosphere is balanced by radiative cooling to space. Second, we've simplified this setup even further by looking at just the purely dry case and using direct numerical simulations to look at the vortexes that form in rotating Rayleigh-Benard convection. And then third, I may or may not get to this part today, but I've worked on solutions to a model of the outer wind structure of hurricanes that applies far away from the storm center, that exploits mass continuity constraints and is just based on dry fluid dynamics. And I've got 3 short spoiler results slides that show where each of these projects goes before getting into more detail. So the first and most important punchline, what I hope you remember out of this talk, if you haven't seen the result before, is largely summarized in this figure and the title of this slide. So dry hurricanes, that is hurricanes without any water in them at all, can readily form in simulations of the atmosphere that are rotating radiative convective equilibrium over a dry surface. These storms shown on the right are less intense, like a map of them shown on the right, are less intense than their normal moist counterparts shown on the left. They have smaller outer sizes, but they have bigger eyes or regions of maximum winds relative to those outer sizes than the moist storms do. This is talked about in a paper by myself and a collaborator, Dan Shavas, a few years ago, the Journal of the Atmospheric Sciences. Second, much more recently, in work that a graduate student of mine has done, we found hurricane-like vortexes in the even simpler setup of rotating Rayleigh-Benard convection for certain parts of dimensionless parameter space. So these have shown up really clearly only in one combination of thermal boundary conditions that uses a simple representation of flow-enhanced heat fluxes at the bottom boundary and an insulating top boundary. But there are some glimmers of potential long-lived vortexes, structures that spin and rotate and look like hurricanes in other setups, including this one at the middle left, which is a constant heat flux at the bottom boundary above an insulating top. And third, I've come up with new analytic solutions to the outer wind model formulated by Emanuel in 2004, which was formulated as a differential equation with no known solution. The possible implications of this can now constrain behavior of different storm variables radius of maximum wind, the maximum wind speeds, and the outer radius under climate change. This is in a paper in GRL earlier this year. So this talk will have 4 main parts. First, I'm going to give some background about hurricanes, tropical cyclones, and how you can make them in numerical models of the atmosphere. And then I'll move on to talk about the 3 projects that I've very briefly summarized in the last few slides. Okay, so the essence of a hurricane or a tropical cyclone, I'm going to use the terms interchangeably today, lies in its energy source, which is convection driven by a supply of moisture and or heat from the surface. So tropical cyclones are fundamentally different from mid-latitude extratropical storms because they draw their energy from the surface. They like symmetry. They like a lack of wind shear or vertical variation of the horizontal winds. They're inherently diabatic phenomena that require air to move across isotropes or surfaces of potential temperature as it circulates through the storm. On the other hand, mid-latitude storms draw their energy from large-scale horizontal temperature contrasts. They're inherently asymmetric. They form most readily in environments with strong, balanced wind shear, and the flow in them can largely be viewed as an exchange, an adiabatic exchange of cold air moving downwards and equatorwards and warm air moving upwards and polewards. Hurricanes in the present climate are mostly limited to the tropics because only in the tropics are these combined factors of weak horizontal temperature gradients and relatedly weak vertical wind shear, and also large disequilibria or differences between the energy of the surface and the energy of the air just above the surface found. Hurricanes also require some amount of planetary rotation to project onto the local vertical direction, or some amount of Coriolis acceleration. And so there's a barrier to genesis right near the equator where there's no component of vertical rotation from the planet, from the Earth. So there are some rare exceptions to hurricanes being a purely tropical phenomenon. There are some that aren't marked on this plot that vortexes that are like hurricanes that are sometimes found in the Mediterranean called metacanes, and there are some high latitude vortexes in the polar seas, especially off of Norway, called polar lows that look sort of like hurricanes, but these are the sort of official tropical cyclones based on global tracks from different agencies. So I talked briefly about the notion that hurricanes are diabatic, requiring heat throughput to operate, and this works best in the current climate in the tropics. I want to go into this idea a little bit more. So the diabatic essence of tropical cyclones means that they can theoretically reach a steady state where the overturning circulation in radius height space looks sort of like a heat engine. And so each of these 3 panels is just showing this secondary circulation or this overturning circulation. The primary circulation is used as a term to describe the swirling winds, whereas this is the flow in radius height space. And so the inflow in radius height space starts with air near the surface, far away from the storm. You move inward along a trajectory near the surface, picking up heat and moisture and decompressing as you move towards the center or low pressure of the storm, the eye wall and the eye. You move upwards and outwards in the deep convective clouds of the eye wall and the subsequent outflow near the tropopause. And then there's a sort of return leg that matters a little less. That's a combination of air losing heat by radiation and sinking down towards the surface. In sort of more conventional thermodynamic coordinates of pressure and volume, you can map this out as being a trajectory from point A to B as starting out at high pressure and comparatively low volume, and then expanding isothermally or roughly isothermally on the leg from A to B in the inflow leg near the surface, expanding moist adiabatically on the leg from B to C as you go, as you really decrease the volume of air and the pressure of the air. And then, increase the volume of the air and decrease the pressure. And then going back from point C to point A, increasing the density, decreasing the volume, and having a combination of radiative heat loss and subsidence. You can also view this in temperature, moist entropy coordinates, and it's more simply just like a triangle in that space. So the points from A to B are an isothermal expansion, from B to C are a moist adiabatic loss of temperature or expansion as well. And then going from C to A is a combination of heat loss and compression. But going back to higher temperatures at lower at higher pressures. So there's a very nice body of theory by Emanuel that looks at this in terms of potential intensity, which sets a speed limit for hurricane winds. And the idea is to look at small subcycles of air movement near the core of the storm, near the eye wall. And in particular, if you take this thermodynamic subcycle from B prime to B to C prime and back near the center of the storm, the heat input rate per unit mass of air from surface heat exchange is proportional to an enthalpy exchange coefficient, CK, multiplied by the swirling wind speeds at the surface, V, and then multiplied by the difference in moist enthalpy between the surface itself and the air just a little above the surface. That's K naught star minus K. And the potential work that can be done by this heat input Q is related to some efficiency multiplied by Q. And the efficiency, if you take it to be a Carnot cycle, has efficiency surface temperature minus outflow temperature divided by the surface temperature. So around 300 Kelvin here, 200 Kelvin here, that would be around a third, 30% efficient. And then you can equate this so this is the potential work done per unit mass, this efficiency multiplied by heat throughput. If you assume that this all goes into frictional dissipation of winds near the surface, at the surface, which is a drag coefficient multiplied by the cube of the velocity, and you equate those two, so setting CdV cubed equal to this efficiency times heat input per unit mass, then you can solve for the wind speed, the maximum wind speed you can get from that and label it a potential intensity, Vp. And it's proportional to a ratio of exchange coefficients, this thermodynamic efficiency, and then a difference between a thermodynamic disequilibrium at the surface, all square rooted. So there's a major body of work by Emanuel on this, and it's really, I think, a nice accomplishment in atmospheric science. The thing that I want to note about this, and as a motivation for the work that I've done, is that nothing in the theory that I just presented precludes dry or semi-dry hurricanes. Those would all potentially have well-defined secondary circulations, could act like heat engines, could behave very similarly. So if we try to define hurricanes as broadly as possible, we can see that this theory of hurricanes as axisymmetric, warm core convective cyclones that act like heat engines and tend to generate swirling winds under the influence of rotation. Nothing about that theory intrinsically requires moisture. It may very much require moisture for the conditions of Earth's atmosphere at present, but not in general. So dry hurricanes would be driven by a temperature jump at the surface, or a surface to air temperature drop, like you have over a parking lot or a beach on a really hot sunny day, rather than a humidity jump as over tropical oceans. Dry hurricanes would be driven by sensible heat fluxes of inflowing air, literally heating up the inflowing air rather than mostly moistening it. And they would have to be driven by deep troposphere spanning dry convection near their cores rather than deep cloudy moist convection. And this is exactly the features that I just described, a big temperature jump, sensible heat fluxes dominating, and troposphere spanning moist dry convection are exactly how the cyclone simulated in the Moroyets et al. Paper works. I want to talk about going a bit beyond that work, first by working in a 3D model, also by using a closed domain rather than one that's open on the outer walls, and also by spanning a range of different surface conditions between dry and moist, and then trying to simplify things even further. So in order to do these simulations, we need a sort of a minimal model setup that allows hurricanes to form naturally, spontaneously, without needing to sort of put them in and see how they evolve. And that minimal model starts with the notion of radiative convective equilibrium. So the real Earth has variations in surface temperature, continents, land surface properties, and spherical geometry. Most of those are unnecessary complications for thinking about this work. So the way we're going to set up simulations of hurricane worlds is by looking at an atmosphere that is in radiative convective equilibrium and just takes account in vertical variations of atmospheric properties in the vertical direction. So we imagine that every location in the horizontal initially has the same surface properties on average and the same atmospheric profile. So radiative convective equilibrium in the atmosphere is generally defined by a troposphere that occupies most of the mass of the atmosphere and which is mixed by convection. Usually in our thinking about Earth's atmosphere, that's moist convection above the lifted condensation level, but it could be dry convection in a different setup. And also an overlying stratosphere that's in radiative equilibrium and stably stratified to convection. So from an atmospheric energy balance perspective, the troposphere needs to be convective in order to balance its radiative cooling. The atmospheric water balance requires that surface evaporation equal surface precipitation to the surface. So dry radiative convective equilibrium looks a lot like this, but there's no cartoon clouds left. And the tropospheric heat transport switches from being rising warm and moist air in storms to just rising hot air and sinking cold air. And the stratification in dry radiative convective equilibrium sort of switches from this moist adiabat to something that's a dry adiabat. So in order to get hurricanes from RCE, we need one extra ingredient, and that extra ingredient is rotation. So this allows areas which develop a lot of updrafts and convergence near the surface to start to spin up and swirling circulations. And since these swirling circulations pull more heat out of the surface, or more heat and moisture out of the surface, they can self-amplify because the strong surface winds lead to more heating of the air near the center of an incipient vortex that makes more rising motion, which amplifies the inflow and so on, and amplifies the swirling winds and so on. So what you end up in this case with is a world filled up with hurricanes, or a tropical cyclone world, or TC world. I think these are fun to look at and cool. It's good that we don't live in such a world, obviously. Okay. So with that sort of background covered, this brings me to the first research part of the talk, which is about systematically varying the surface moisture availability in simulations and seeing how the formation and maintenance of cyclones responds to that. Okay, so before I get to some movies and results, I want to give a little more detail about the setup for anyone who's interested. So specifically, we're using a system for atmospheric modeling convection permitting model that's at a high resolution with a horizontal side length of a few kilometers, a grid spacing of a few kilometers, in a very big domain, about 1,000 kilometers on each side. So we're prescribing the tropospheric radiative cooling rate to be a constant of a degree per day, which is close to tropical values. And we're fixing the sea surface temperature in each simulation. I'm going to show results for going from and each simulation is also started from an equilibrated, non-rotating radiative convective equilibrium state with the same boundary conditions. So we're not abruptly going from a moist initial atmosphere to a dry surface or vice versa. So I'm going to show results for going from a moist to dry surface in two ways. The first is by varying the surface wetness, which we call beta. We tune that between 0 and 1. And in the model, it modifies the surface saturation vapor pressure relative to that of pure water at the given fixed sea surface temperature. So beta equals 0 reduces the vapor pressure that the surface has to 0 in the model. And beta equals 1 corresponds to a completely moist surface. The second way to make the surface dry is to make it really cold, because given a total surface enthalpy flux, a colder surface has a greatly reduced importance of the surface latent heat flux, and the saturation vapor pressure goes to 0, goes to very small values as you reduce the surface temperature. So one thing to just note briefly is that this surface wetness parameter is actually physically realizable, and we took our notation from literature about surface hydrology over hypersaline bodies of water. So Raoult's law says that if you've got a mixture of two fluids or two substances, the vapor pressure of a component of that mixture is equal to its molar fraction times the vapor pressure of that pure substance. So if you've got, say, water mixed with a lot of salt or mixed with some other non-volatile fluid, you could, in theory, have an ocean that doesn't evaporate like pure water at all. And in fact, hypersaline water bodies like the Dead Sea or the Great Salt Lake or the Aral Sea evaporate very little compared to what you would have from pure water. So the Dead Sea, for instance, has beta less than 0.5 parts. Okay. So here I'm going to show two movies of how the wind speed evolves in two simulations, one from a moist surface, beta equals 1 on the left, and one from a dry surface, beta equals 0 on the right. The Coriolis parameter is set to a much larger value than in reality here to allow storms and multiple storms to fit into these simulated boxes. Okay, let me play the right-hand one too. So what we see is that storms are going to spin up almost immediately within a few days. The day timer is probably too small for you to see, but this is day 5, 6, 7 on the right, day 8 and 9 on the left, and moist storms are starting to form and interact with each other in this sort of turbulent tropical cyclone world. These, again, are maps of the near-surface wind speed. So you see strong eye walls of storms that have winds of up to 60 meters per second on the left, much broader features that have moderate winds of 20, 30 meters per second on the right in the dry case. So very early and quickly, storms form in dry radiative convective equilibrium. The same happens in moist RC. There are fewer storms. They're more intense. They tend to be bigger. And so the take-home points from looking at this movie, and you can watch it evolve for longer, are that, skipped back the dry one to the beginning. Dry hurricanes readily form and persist in rotating dry radiative convective equilibrium. They tend to have bigger eyes and weaker peak intensities. But very interestingly, even though these systems have very different distributions of surface wind speeds, the average kinetic energy dissipation at the surface, or the domain integral of CdV cubed, is pretty similar for the two cases. So in terms of their structure, dry hurricanes look pretty different than regular moist storms. So this is a map, again, of a snapshot on the left, where there's a moist tropical cyclone world on the top panels and a dry one on the bottom. And the central pressures are much higher. The surface wind speeds are weaker for dry storms than moist ones, shown in the colors and the contours here. If you look at a radius height section shown in the middle panels, and now at the swirling winds or azimuthal winds in colors, you see both storms have a feature of this, eye wall maximum of winds near the surface that decays as you go upwards, decays as you go outwards. But the structure of the warm core is quite different in the moist case, where there's this big upper tropospheric warm anomaly, than in the dry case, where there's just sort of a tropopause dip that's a warm anomaly. And then if you look at the swirling winds at the surface plotted against radius, what's shown here on the top is that different storms in the moist tropical cyclone world can have very different radial structures. They all look similar in a way. They have a very tight, a narrow region of maximum winds going up to the eye wall, and then a long, slow decay of their swirling winds as you go to greater distances from the center or greater radii. But individual storms can look pretty different from one another. And this is showing this small storm with a small radius of maximum winds, which is actually just as intense in max wind speed as this bigger storm over here, shown in blue and dark blue. In the dry tropical cyclone world, on the other hand, all the storms pretty much look the same. They all of these different X's that correspond to tracking different storms have wind radius relationships that look similar to each other. So we also wanted to understand whether the transition between these very different sort of vortex structures is continuous or not, and that's where some things get pretty interesting. So we found that the moist to dry transition is mostly gradual, but then there's also this discontinuity where storms don't form spontaneously at low but non-zero surface wetness. We've tried to understand this and not come to a definitive conclusion, but what we have been able to do is basically take a moist simulation and gradually dry it out. And in that case, you do go continuously through this no storms part of parameter space once you've formed cyclones. And similarly, if you form storms here in dry space and then moisten the surface gradually, you also end up keeping those storms as you pass through this part of parameter space. So what we think is that this is a barrier to spontaneous genesis at low surface wetnesses, but not to storm existence at all. Okay, so and to further characterize that and to look at the moist-dry transition and provide some evidence that storm properties transition relatively continuously between moist and dry limits, we've looked at a few non-dimensional properties of the individual cyclones that form in each simulation. So we've compiled these statistics by looking at all the cyclones in each case and in each simulation from each hourly snapshot of surface pressure and winds, and calculating azimuthal average or average around the swirling dimension of the storm values for each cyclone. And then for these two quantities, one is a ratio of the actual intensity to the potential intensity given by Emanuel's potential intensity theory. And so we see that in this case, the moist storms reach close to their potential intensities, but dry storms are far from that limit. The second parameter is the inner core Rossby number, which is a measure of the force balance in the dynamics of the core of the storm. And so values much greater than 1 correspond to cyclostrophic balance, values order 1 correspond to gradient wind balance, and then values that were much less than 1 would correspond to geostrophic hurricanes, which we don't have in our simulations. So in both the case of varying surface wetness, shown in the top panels here, and varying surface temperature, shown in the bottom ones, the transition in these two non-dimensional parameters from sort of moist storms to dry storms, or on the top, moist storms, warm storms to cold storms, which are also effectively dry, is mostly gradual, with most of the transition in both of these parameters, the ratio of maximum to potential intensity and the inner core Rossby number, happening before you get to this area where storms don't spontaneously form. So the point here is to say that this is sort of a continuous dynamical regime and not something where dry storms are behaving uniquely. In fact, they look really similar to storms at a surface wetness of 40% or 0.4. And finally, we can look in a little more detail at how the swirling winds vary with radius or distance from the storm center. And we found that they're relatively well captured by a two-region wind model that follows a nice paper by Den Chavas, Ninglan, and Emanuel from 2015. And the thing that I just want to point out here is that the winds for moist storms with beta equals 1 here in blue decay comparatively slowly as you go away from storm center when you're far away from the center of the storm. On the other hand, the winds for the dry storm decay somewhat faster, and for semi-dry storms, you have intermediate decay speeds of those winds. This is consistent with a theoretical outer wind model by Emanuel in 2004 that matches the Ekman suction rate into the outer wind part with the radiative subsidence speed, which is the ratio of the radiative cooling rate of air just above the top of the boundary layer to the static stability there, or basically how fast air has to sink through a given environment in order for its radiative cooling rate to just match its adiabatic warming rate. Okay, and so that radiative subsidence speed, W cool, is much larger for the dry simulations than the moist ones because the environment is much closer to a dry adiabatic stratification. And so has much less static stability. The adiabatic warming is much weaker. This is sort of consistent, and I might get to more of this in part 4, but I suspect I'll just leave those as sort of extra slides in case anyone's curious. Okay, so the main results again from this part of the talk: dry hurricanes readily form in rotating radiative convective equilibrium. Their properties differ from moist counterparts. They have weaker peak winds, larger radii of maximum winds relative to their outer size. And the transition appears relatively continuous, except for this intriguing no storms land barrier to spontaneous genesis, which we think might have something interesting to tell us about how genesis processes work in the real world and what barriers to them are, though that remains to be, a lot of that remains to be explored. Okay, so the work that I just talked about came out a few years ago, and it's and one of the projects of a PhD student of mine, Martin Velez-Pardo, that he's trying to follow up on in an even simpler modeling setup is to see if the results still hold in rotating Rayleigh-Benard convection. So the second research part of the talk is on organization of convection in an even simpler model setup. So Rayleigh-Benard convection is this canonical, applied math, engineering, physics problem where you have convection of a homogeneous fluid between two infinite flat plates. So the only thing, the thing that varies here is there are a number of things that can vary in terms of how you make the experiment set up. The classical setup is that you have a bottom plate that's held at a slightly warmer temperature than the top plate by some amount delta T. You're doing this experiment in a gravitational field. The plates are separated by a distance h, and the material properties of the fluid are important. So the thermal diffusivity kappa, the kinematic viscosity nu, the thermal expansivity beta, all those parameters combined with these others to determine two key non-dimensional numbers. The first is the Rayleigh number, which is a metric of how strongly convection is driven by this thermal contrast relative to viscous dissipation. And the second is the Prandtl number, which is a ratio of material properties of the kinematic viscosity to the thermal diffusivity. That Prandtl number is going to be around 1 for our experiments, and so it's not super important. It can vary a lot for drastically different materials like the mantle of the Earth or the plasma of the sun. Adding rotation to this gives a third non-dimensional number, and there are multiple ways to express this. I'll talk about one on the next slide. I'm indicating rotation with this omega as an angular velocity of rotation. And then there's really a fourth non-dimensional number 2 for most practical cases. So simulations or experiments all need to have, by necessity, finite horizontal extent. So you do limit the results you can get based on the aspect ratio that you are able to simulate or do an experiment on, which is the horizontal distance to the vertical distance, gamma, or length of the simulation or experiment divided by the height of the fluid. So you can impose, what I just showed on the last slide is that you can impose to sort of temperature-based boundary conditions. You can also impose flux-based boundary conditions. So you can say, put a fixed amount of heat through this cell, and instead of having a temperature difference define how strongly convection is being forced, have a heat flux define how strongly you're forcing convection. And with flux-based boundary conditions, the parameters change a little bit. You end up with a flux Rayleigh number that's proportional to the buoyancy flux that you're putting through the layer, which is a metric of both the heat flux and how much buoyancy the fluid carries per unit heat carried. The fourth power of the layer depth, and then inversely as the kinematic viscosity and the thermal diffusivity squared. So that becomes the measure of how strongly convection is driven, the flux Rayleigh number. The Prandtl number is the same. And then there's the non-dimensional number corresponding to the importance of rotation is what I want to talk about a little bit. That's the convective Rossby number. It's essentially a ratio of the rotational time scale to the convective time scale. So for Earth's atmosphere, convection is fast relative to rotation. It takes maybe an hour for air to ascend through a thunderstorm from the surface to the tropopause, or less in many cases, compared to the many-hour time scale of rotation. In the ocean, on the other hand, people think about this a lot because it takes sinking plumes, can take them many hours or order days to sink from the surface to a few kilometers depth in places where deep convective chimneys form in, say, the Labrador Sea. So low convective Rossby number corresponds to the convective Rossby number is proportional to the ratio of the time scale it takes for free convecting fluid to go from the bottom to the top of the fluid of the layer of depth h, and proportional to that divided by the rotational time scale, or the rotational rate, I should say. The limit of low convective Rossby number, or convective Rossby number quite a bit less than 1, corresponds to rotationally controlled convection, where any sort of overturning cell, any sort of convective overturning cell strongly feels rotation. The limit of large convective Rossby number can be that individual convective cells don't feel rotation, but collective effects of multiple convective cells do, if their circulation timescales are of an individual convective cell is fast compared to rotation, but broader overturning circulation timescales are slow. That's the sort of limit we're interested in. So where we think we should look at in parameter space to look for these hurricane-like vortices is the limit of strongly turbulent convection. So the flux Rayleigh number is large as possible. A large aspect ratio, where we have a large horizontal extent compared to the depth of the fluid. And a limit where we have a convective Rossby number that's somewhat greater than 1, where individual convective plumes and thermals are not controlled by rotation, but the large-scale circulations from their collective effects can feel rotation. So what we found in these simulations is that the organization of circulations and convection is very strongly sensitive to the thermal boundary conditions. So the classic choice of fixed temperature boundary conditions that I showed initially is at the bottom right here. And you see very little large-scale circulation emerging. So this is a map of the wind speeds, of the flow speeds at 20% of the layer depth. The parameters we're using here are a flux Rayleigh number of 10 to the 9th, a convective Rossby number of 2, and an aspect ratio of 16. So these are doubly periodic boxes where the horizontal extent is 16 times the depth of the convecting layer. So there's no large-scale persistent structures that form in this fixed temperature boundary condition case. Where we do see a clear hurricane-like vortex forming is a situation where we have a flux-based bottom boundary condition where the heat flux is enhanced by a flow near the bottom boundary. So we've called that a parameterized flow speed enhancement of the flux. And then on the top, an insulating boundary. So this is the most atmospheric-like setup we've contrived. We also see some weaker persistent vortexes emerge that are less clearly hurricane-like in a setup where there's a constant heat flux on the bottom above an insulating top. And so just to zoom in on the vortex shown at the top left here that looks really clearly hurricane-like, it's got a warm core. So this top panel is showing temperature anomalies relative to the domain in height, radius space. It's relatively axisymmetric. It has similar winds on all sides of it. And it has a bottom intensified cyclonic flow. So that's showing in the bottom here, the swirling winds are shown in green to white to brown. The temperature anomalies shown at the top here show that this cyclone has a warm core and then it gets colder outside. And that there's an overturning circulation that moves, fluid into the middle of the storm and then out. So this flow enhancement of the fluxes is something we've had to sort of to tweak into this setup. It might occur without parameterization if you either had a much higher flux Rayleigh number, had much more turbulent convection, or if you have rough surfaces, and as in nature, it's possible that you get this natural flow enhancement of the surface fluxes. But that's something that's seemed to be important. Okay, so I'm going to play a movie here, and then I think I'll skip to conclusions since it's getting to be later in the hour. So what we found here is this emergence of dry hurricane-like vortexes in a very, very simple model setup, rotating Rayleigh-Benard convection with some tweaks to the boundary conditions that are pretty minor. The two key ingredients seem to be that the bottom and top boundaries be asymmetric in terms of their thermal boundary condition, and that the fluxes, surface fluxes at the bottom need to be enhanced by the flow speeds there. And this was in a paper that grad student of mine and I published earlier in the year in Journal of Atmospheric Science, VLS Pardo and Cronin in 2023. So I think I'm going to skip over this final section on the outer wind model. And if you're curious, you can look at the GROL paper on it, Cronin 2023, that I'll have in the conclusions. Overall, we found that the dry hurricanes readily form in rotating radiative convective equilibrium. They have weaker peak winds and a different structure than we expect from regular moist storms. And we found that hurricane-like vortexes can also form in rotating Rayleigh-Benard convection, but it's sensitive to thermal boundary conditions and seems to require some tweaking to give an enhanced flux due to increased flow speeds. The thing I didn't talk about was this GRL paper on outer wind model, where analytic solutions to the outer wind model of Emanuel 2004, I think really help us understand differences in storm structure as you go from this moist to dry limit, and why vortexes can look different in the moist case, but sort of all collapse onto one structure in the dry case. Okay, so taking a step back, I also want to note that most idealized modeling work that's done on hurricanes is focused on realistic tropical cyclones. So this is a schematic of 3 dimensions of parameter space, surface temperature going up, surface wetness going this way, rotation rate going this way. Most simulations that people have done have focused on these sort of realistic territory near these black lines around realistic rotation rate, realistic moisture availability of 1, realistic tropical current day sea surface temperatures. Some of the results that I've shown today, these green lines span a small range in this parameter space, but a sort of different range. We've seen that there's, you can get to a dry surface in multiple different ways, either by drying out surface physically or cooling it off by a lot. The results of Martin's work on rotating Rayleigh-Benard convection sort of lie in a completely different parameter space, separate but related, of flux Rayleigh number, convective Rossby number, aspect ratio, which are more fundamental parameters to convection in some ways, but where moisture is not included. So they suggest that other dimensions of parameter space that aren't listed here, such as surface roughness, the upper boundary condition might be important too. This gray line here is included based on other work by Emanuel that suggests that at very high sea surface temperatures, there's theoretical possibility to get really weird vortexes called hypercanes that have vanishing like a vacuum at their center. In any case, to close, I think that there's a whole lot of room to push the boundaries of what we do in idealized simulation and theory of hurricanes. And there's a lot to learn and numerous signs that there's quite interesting territory in many directions. So thanks for your time. Happy to take questions.
Thanks. So if anyone has any questions, you can go ahead and raise your hand or just go ahead and unmute yourself. You're all able to do that. Or you can type it in the chat if you don't have a microphone. Go ahead, Thaddeus.
Yeah.
Thanks. Yeah, thanks for the great talk, Tim. I have a couple new papers I should read. My question for you is, so right, there's this huge parameter space based off of Earth, and you're kind of now pushing in a direction that's in many ways going away from, Earth-like conditions, especially with surface wetness. And I'm wondering, right, you think about this moist to dry continuum, but I'm wondering about conditions where the atmosphere might be even more moist than Earth, or even Earth with a higher sea surface temperature. I'm thinking about conditions where, for example, like water vapor becomes a dominant gas in the atmosphere, and of course that would affect convection. Have you thought about how this might affect TC formation? If you have a case with less background inert gas and more condensable gas?
Yeah, so that's a good question. I guess the one place where sort of work has touched on that more, these are sort of solutions to this theoretical outer wind model, and a key property there is the the radiative subsidence speed. If you go to an atmosphere that has an even more stable lower troposphere, because it's got the moist adiabat is juicier, it has a more of an increase in potential temperature with height. You sort of push more towards this moist limit, and the thing that happens there is you get even longer sort of outer tails of the winds, or a bigger ratio of the sort of outer calm storm where the winds build up slowly as you go inwards to the eye wall. So the eye wall can get to be a really small sort of component of the storms as you go towards that moist limit, which makes them even harder to simulate in a way, because you've got to do this. You've got to have this huge domain to sort of have the air catchment that where air is going to flow into the storms. It's not the only thing that can happen as you go to higher temperature. This hypercane stuff is also pretty fascinating. No one's ever simulated that in a 3D model, and it's probably very difficult to do. But there's this sort of increasing sea surface temperature. There's stuff I could speculate about that too. But the main thing that my work points to is just the behavior of the outer wind model is likely to change in a way that gives you an even smaller ratio of the inner core to the outer size of the storm.
Thank you.
Any other questions? Give another minute.
Yeah. I have a quick question, Tim.
Yeah. Hey, Ben.
Yeah, it's Ben. I just had a question about the eye. Is it still going to have as rapid a downward flow? Because I thought a lot of that was driven by condensational heating aloft, causing a vertical pressure gradient. So what happens to that in the dry case?
Are you thinking about the sort of downward flow outside the storm, or
in the eye itself, the downward
in the eye
flow?
itself? Yeah. So I haven't actually looked at what the flow in the eye itself looks like very much in the dry simulation. So it's a good question. I think that you have competing things that you're sort of lacking condensational heating in the eye wall, right? But you also have a much weaker, like there's almost no static stability to fight against for pushing air downwards. So it takes very little to sort of be thermodynamically consistent with air sinking in the middle of the storm. But I haven't looked at that in detail at these simulations.
Thanks.
Yeah.
Any other questions before we wrap up? Okay, well, unless someone interrupts me, which you can definitely do, I think we are good for this seminar. Thank you so much to Professor Cronin for giving us this great talk. This was great. And just as a reminder to everybody, it will be on our YouTube channel in just a couple of days. So if you want to review anything, it is all there. So yeah, thank you to everybody for showing up. We are going to continue our seminar series next week. I know there's a federal holiday coming up. I don't think that's on a Monday though. So yeah, next Monday at 2 o'clock. Thank you, everybody. Have a good afternoon.
Okay, thanks very much.